This video will demonstrate how to design a Beam over HSS connection in VAConnect. Let's get started. In this example, the end of a W18x50 beam will be connected to the top of a HSS 7x7 by 1/4 inch column. The beam is loaded with both dead load and live load that will transfer axial load and moment to the top of the column. Applied moment and axial load are resolved into two axial forces determined from statics that are transferred across the beam flange to cap plate interface. Compression forces are assumed to act at the face of the HSS, whereas tensile forces act at the center of the bolts as shown in the image. Depending on the magnitude and direction of the applied loads, the forces that are transferred across the beam flange to cap plate interface may both be in compression or both be in tension. When both forces are compressive, only one wall of the HSS is considered to resist each of the compressive forces. We will start out in VAConnect by adjusting the geometry of the connection. Selecting the beam, a W18x50 will be chosen from the shape database, and in the material database we will use A992 grade 50 steel. Next, we will select the column and choose a HSS 7x7 by 1/4 inch member from the database, and then select ASTM A500 grade C with Fy equals 50 KSI for the column. Now with the geometry roughed in, we can look at the project status to see that there is a warning for the detailing. Clicking on this shows the warning which says that the out-of-plane motion at the top of the HSS must be restrained by adding a stiffener to the web or by another method, and that Part 2 of the AISC manual has more information and details for beams framing continuously over columns. Selecting the beam and adding a stability stiffener removes the warning. With the detailing now okay, let's move on to apply loads to the connection. We will apply the axial load and moment for the dead load case and the axial load and moment for the live load case. Clicking on the load case manager shows that the load combinations are automatically generated for the selected building code. Note, Beam over HSS connections are checked per the AISC Steel Design Guide 24 and the AISC 360 Design Specification. The scope of the AISC Design Guide 24 is restricted to non-seismic applications. Therefore, if we enter a seismic load for the connection, we get a warning saying seismic loads are applied to the connection which are not permitted per Design Guide 24. With the load specified for the connection, we can now turn our attention to the project status to see the various limit states for the bolts, welds, beam web, and HSS walls that are automatically checked. Immediately, we see that all of the limit states, with the exception of one, are passing, meaning that we can probably better optimize our connection. First, let's try to reduce the thickness of the cap plate to 3/8 of an inch. Upon doing so, the HSS wall local yield limit state fails. Clicking on this limit state shows that the local yield capacity depends on the thickness of the beams, flange, and web, the thickness of the HSS wall, and the thickness of the cap plate. Therefore, we cannot reduce the cap plate thickness without increasing the size of the HSS or W shape, which likely would not be economical. Next, let's look at the bolt tension with prying limit state. This limit state calculates the available tension strength of the bolts considering the effects of prying from the beam flange, and calculates available strength of the bolts considering the effects of prying from the cap plate, and uses the worst case to determine the capacity for the limit state. Currently, the capacity is controlled by the available strength of the bolts considering cap plate prying. Since alpha prime is greater than 1, the connection has insufficient strength to develop the full bolt available tensile strength. Therefore, the tensile strength of the bolt, phi Tn, is reduced by a factor of Q, and yet the available strength considering prying still exceeds the required strength for the bolt. Reducing the bolt size to 0.5 inches in diameter causes alpha prime to reduce to a value of less than 1 but greater than 0, meaning that the connection has significant strength to develop the full bolt available tensile strength, but has insufficient strength to prevent prying. Therefore, the tensile strength of the bolt VTN is reduced by the factor of Q, and yet this available strength considering prying still exceeds the required strength for the bolt, and the limit state still passes. Next, we notice that the weld between the HSS and cap plate has a low unity of about 0.5. According to the design guide, to determine the length of the weld, a 45-degree maximum dispersion angle is assumed from the bolts to the face of the HSS. This limit state checks the shear strength of the fillet weld itself and the base metal capacity of both the HSS and the cap plate. If we try to reduce the size of the weld, the detailing check fails and says that we do not meet the minimum size requirements of the fillet weld according to the AISC 360 specification. Looking at the limit states for beam weld, local yield, and crippling, the unity values are 0.55 and 0.525 respectively. We also see that the beam web compression buckling is at 1.023. Currently, the column is located along the length of the beam, whereas in reality, the column will be located at the right end of the beam. Upon moving the column to the end of the beam, the unity value for beam web yield increases from 0.55 to 0.809 since the compressive force is now 11.5 inches away from the end of the beam, which is less than the beam's depth of 18 inches. This decreases the capacity of the beam for web local yielding. Note, since this limit state is applicable for both tension and compression, VAConnect automatically checks the capacity for both and reports the controlling case. Finally, let's look at beam web compression buckling, which is just failing at 2.3% above unity. According to the AISC 360 specification, web compression buckling applies to a pair of compressive concentrated forces at both flanges of the member at the same location. Since our loads for this example come from a distributed dead load and live load, we can use engineering judgment to determine that this particular limit state is not applicable. With the design complete, we can switch the report view to easily create a report to document our work. A concise design summary is automatically generated, showing the unity value for each limit state. Also, we can add detailed reports showing the calculations for each limit state, or we can add summary tables for each limit to the report. In just a few minutes, we have used VAConnect to create an optimal design for our Beam over HSS connection and produce a report to document our work. Thanks for watching and have a great day.